All right, so I'm going to do a lecture on odds. This is actually the second lecture today I'm doing on section 4.2 because the first one was more or less disastrous, I guess. I just wasn't happy with it at all. And the nice thing about the videos is if it's really awful, I can re-record it and nobody will ever know the awfulness that I can do. And it was so awful that I think I actually swore at myself. And I've never swore in front of my parents, and I generally don't swear, but I believe I called myself an effing idiot. So hopefully this is going to redeem myself, because there's a lot of things that I knew I should have said that I didn't say, and so this is take two. Hopefully this is a reasonable lecture, and if it's still awful, then you can tell me that it's awful. So the title of the section is odds, and odds are a fraction that compares different outcomes, and it splits a sample space into sample space that fit the criteria, and which we call favorable outcomes, and unfavorable outcomes. So for a particular experiment, I can't even spell favorable. We're going to take a sample space and break it down into favorable and unfavorable subsets. For example, if I was concerned with the experiment of rolling a single dice, a single six-sided dice, and recording the number that comes on the face of the dice, the sample space for that would be 1, 2, 3, 4, 5, and 6. If I was asked an odds question about that sample space, then I'm going to separate the sample space into the items in the sample space that fit the criteria and the items in the sample space that don't fit the criteria. For instance, if I was asked to compute the odds in favor, and we'll talk more about what in favor means in a second, of rolling a 5, I would need to break up the sample space into two categories: those items in the sample space that count as rolling a 5, and those items in the sample space that don't count as rolling a 5. This would be favorable and unfavorable. So to do odds, I have to be able to visualize an entire sample space, and then I need to break up the sample space into favorable, meeting the criteria, and unfavorable, not meeting the criteria. And in terms of rolling a 5, the only number in the sample space that would be considered favorable, that would fit the criteria of rolling a 5, would be rolling the number 5. Rolling the numbers 1, 2, 3, 4, and 6 would be considered not rolling a 5. So I'm going to get deeper into odds here and actually compute odds, but in order to do odds successfully, you have to know the sample space that the problem is referring to, and you need to be able to segregate or segment the sample space into the elements in the sample space that fit the criteria and the elements of the sample space that don't fit the criteria. If you can do that, then you can compute the odds. So if you can visualize the sample space, understand the elements in the sample space that fit the criteria and that don't fit the criteria, you'll be able to do all the odds problems in this section perfectly. So I'll dig into the section, and this is just the briefest warm-up. It's not going to help you do any of the problems perfectly, but it's just kind of the groundwork. So odds are fractions that compare. It's a ratio. A ratio means a fraction, and it compares the number of favorable outcomes to the number of unfavorable outcomes. There's two kinds of odds that we'll study: odds against an event happening and odds in favor of an event happening. If you go to Vegas and you look up on a board and they give you the odds for the Cardinals to win the Super Bowl, and it says it's 35-1 that the Arizona Cardinals win the Super Bowl, that's going to be odds against. Mostly when you read odds anywhere, they're odds against as opposed to odds in favor. And as we get deeper into this section, I'll show you the difference between odds against and odds in favor and how to compute each. So technically, the odds against an event, which are the more common odds, is a fraction or a ratio that compares the probability that the event does not occur to the probability that the event does occur. And so the odds against an event can be computed by computing two probabilities and dividing them. The probability that's going to go in the numerator is the probability that the event does not occur. The probability that goes in the denominator is the probability that the event does occur. And then I could abbreviate these a little bit, but I won't right now. So to find odds by the formula, you have to be able to compute the probability that the event does occur and the probability the event does not occur. If you can't compute probabilities, then odds are a little bit clunky to compute. So this whole sheet right here just says the odds against, which are more common, is a ratio. A ratio is a fraction, and it's a ratio of probabilities. The probabilities that we form the ratio of is the probability of the event not happening divided by the probability of the event happening. To do that in the case of a specific example, so a single six-sided dice is rolled one time and the number face up is recorded. Determine the odds against rolling a 2. Well, in order to do odds, I have to be able to do probabilities. In order to do probabilities, I need to know the sample space. So the sample space for rolling a single six-sided dice is any of the numbers 1 through 6 can come up. We did that in section 4.1. Now, if I want to find the odds against rolling a 2, then I have to compute two probabilities. The numerator is going to be the probability of the event not happening, and the denominator is going to be the probability of the event actually happening. So the probability, or the odds, can be computed by forming a fraction, and the numerator and the denominator of a fraction each have a separate probability. In the numerator, since it's against, I'm going to put the probability of not rolling a 2 because that's against and I want the event not happening. And then the denominator is going to be the probability of actually the event happening, in this case rolling a 2. So the odds against an event can be computed by making a fraction, and I want to separate the sample space into rolling a 2 and not rolling a 2 because the event is rolling a 2. And when it's odds against, the not rolling a 2 part of it goes in the numerator and the rolling a 2 part of it goes in the denominator. So I'm going to form two fractions. The numerator is going to be the probability of not rolling a 2. And the probability of not rolling a 2 is going to be something over 6 because 6 different numbers can come up, and the numbers in the sample space that qualify as not rolling a 2 are the numbers 1, 3, 4, 5, and 6. So the numerator here, the probability of not rolling a 2, is 5 and 6. The denominator of my odds computation needs to have the probability of rolling a 2, and of the 6 things that can come up in the sample space, one of them is a 2, so the probability of actually rolling a 2 is 1 in 6. So the formal way of computing the odds against rolling a 2 is to form a fraction, and the numerator and the denominator have separate probabilities, because and those probabilities need to separate the sample space into rolling a 2 and not rolling a 2. Since it's against, the not is in the numerator. So this is the fraction that I need to compute, and that's hard, so I'm going to write this differently. I'm going to write this as 5 and 6 divided by 1 and 6, because any fraction can be written as a division sign, so I rewrote this as a division. And now I can invert and multiply. So this is 5 and 6 times 6 and 1. My nephew, who's in 7th grade, he couldn't reduce this so well. He would just multiply it and go 5 times 6 is 30. 6 times 1 is 6. And then he'd reduce this to 5. And when you're doing odds, you can't leave out a denominator. So I'm going to reduce this to 5 over 1. So the odds against rolling a 2 is 5 to 1. Usually when you see odds, they are odds against, and usually they're not shown as fractions. So for an answer, it would be okay to say the odds against rolling a 2 is the fraction 5 over 1, but it would be odd. The more common ways to write odds is have the two numbers separated by the word 2, or have the numbers separated by a colon. But each one of these three forms of the fraction 5 over 1 would be acceptable for the answer, what are the odds against rolling a 2? So that's the formal way to compute odds. Quite honestly, that's kind of not that desirable, not that easy to do. And there's an easier way to compute odds, much easier way to compute odds. So I'm going to do the easier way. I'm going to revisit this problem and do it the easier way, and then the rest of the problems in this section I'll do the easier way. So the correct way, the proper way to do odds against is to form two fractions, to form a fraction and have the numerator contain one probability, the denominator contain another probability. But that's not, like I said, not the most desirable way to do this. So the next thing I want to do is I want to do a shortcut method to find the odds against rolling a 2. So the odds against rolling a 2 are 5 to 1. No matter how I do them, the formal definition of finding the odds, forming a fraction that has two probabilities, a probability in the numerator and a probability in the denominator, is the proper way to find odds, but not probably the most desirable way to find odds. The easier way to find odds, which is the way I'm going to do exclusively in this section, is this way. So same problem, same answer. I need to separate the sample space. So the sample space for rolling a 2, the sample space for rolling a 6-sided dice is rolling the numbers 1, 2, 3, 4, 5, and 6. And if I want to find the odds against rolling a 2, I need to fragment the sample space up into two groups. The first group is going to be not a 2. The second group is going to be a 2. So I'm breaking up the sample space based on the event that's described in the problem, rolling a 2. Because it's against, I'm going to put the not 2's first and the 2's second. So the numbers in the sample space that aren't 2's are 1, 3, 4, 5, and 6. The numbers in the sample space that are 2 is the number 2. Now I'm just going to count. So the odds against rolling a 2 are the 5 items in the sample space that aren't 2, followed by a colon, and then the 1 item in the sample space that is a 2. That's the way I'm going to do odds consistently. And so if I'm asked to find the odds against an event, on either side of a colon, I'm going to fragment the sample space into the items in the sample space that don't make up that event, and then the items that do make up that event. That might not be enough, but we'll do enough of these that eventually it will be enough. This next sheet says odds in favor are just the reciprocal of odds against, and when I do it the shortcut way, so when I do odds against, I'm going to form a ratio, and on the left side of the colon I'm going to put anything in the sample space that doesn't fit the criteria, And to the right of the colon, I'm going to put anything in the sample, any element of the sample space that fits the criteria. When we do odds for, it's not going to really, our odds in favor, for and in favor I'll use interchangeably. It's just going to be the flip. So I'm going to get the answer the same way by forming a ratio, which is two numbers separated by a colon. To the left of the colon, I'm going to put the number of items in the sample space that fit the criteria of the event that's described, and on the other side of the colon, I'm going to put the elements, or the number of elements that don't fit the criteria, and they're just flipped of each other. If you know the odds against, you get the odds in favor by flipping them. If you know the odds in favor, you get the odds against by flipping them. And these formulas I'm just not going to use because they're harder to use, and they don't really serve any really benefit. So, next example, a single six-sided dice is rolled, and I want to find the odds in favor of rolling a 2 on one roll of the dice. So my sample space, I'm rolling a single six-sided dice, and what can happen is I can get any one of the numbers 1, 2, 3, 4, 5, or 6. I want to find now the odds in favor of rolling a 2. So I need to break up the sample space into R2s and R not 2s because the event in question is rolling a 2. So, and because it's in favor, the R comes first and the not comes second. Well, now I'm going to need to look at my sample space. The ones that are 2 is just the 2. The ones that aren't 2 is the 1, 3, 4, 5, and the 6. So the odds in favor of rolling a 2, there's one element in the sample space that is a 2, followed by a colon, and there's 1, 2, 3, 4, 5 elements in the sample space that aren't a 2. It should always be the case when you do an odds that the two numbers that you put in add up to the number of items in the sample space. So when I'm doing odds in favor or odds against, when I'm rolling a single dice, because there's 6 different outcomes that are possible, my two numbers should add up to 6. Alright, so I'm going to walk you through one a little bit. I won't do the whole problem number 1, but I'll do maybe A and C and let you do B and D, because I don't know that there's enough done yet for you to be able to do number 1. So Anne has some bills in her wallet, and Anne's wallet has this. It has 1, 2, 3, 4, 5, 6, 7 ones. It has 2 5s. It has 4 10s. And 1 20. So these are the bills in Anne's wallet. And she's passing a volunteer at some Salvation Army donation, probably bell ringing kettle person, and she's going to reach into her wallet and she's going to pluck out 1 bill. Within question 1, there's a probability question, there's 2 probability questions, and there's 2 odds questions. Probabilities and odds are similar, but they're different. And apparently Sheldon Cooper from the Big Bang Theory doesn't know the difference, because in a recent episode of Big Bang Theory, Sheldon did a computation and said it was odds, but his answer was a probability, which for me was fun because it's kind of a math geek show, and I was surprised that the writers let him make that error. But anyways, so the first 2 parts of number 1 are probability questions, and in probability questions, the denominator is going to be the number of items in the sample space. So Anne can pick any one of these 14 bills. So in part A of number 1, the denominator for a probability is going to be 14, because when she's selecting a bill, she can pick any one of the 14 bills she has in her wallet. The numerator is going to be the number of bills that fit the criteria that they're a $5 bill. Well, the numerator for part A is going to be 2, because she has 2 bills in her wallets that are $5 bills. Generally, when we have probabilities, we form fractions and we reduce the fraction. So for 1A, I'd say the probability that she selects a $5 bill is 1 in 7. If I flip back to my answer for 1A, I get 1 in 7 for the probability. The next thing I'm going to do is part C, and I'll leave you part B and D. So I'm going to find the odds in favor of her selecting a $5 bill. So to do the odds in favor, I need to separate the sample space into $5 bills and not $5 bills. Because it's favor, the not's going to go after the colon. So for part C, I need to fragment the sample space into $5 bills followed by a colon and not $5 bills. If it was odds against, I'd have not $5 bills, then $5 bills. And the reason I'm segmenting it by $5 bills is because that's what I'm worried about here. And so in my sample space, there's the $5 bills, and then the not $5 bills are the 1, 2, 3, 4, 5, 6, 7 ones, 4 10s, and a 20. So my odds in favor of selecting a $5 bill are the 2 $5 bills followed by a colon, and then the rest of the bills that aren't 5s. So there's 7 1s, 8, 9, 10, 11, and 12. So in probability questions, the denominator is going to be the total number of items in the sample space before you reduce, which is 14. In odds questions, the two numbers that you put before you reduce, if you reduce, have to add up to the denominator. So my numbers had to add up to 14 here. So the odds in favor, I would say it's 2 colon 12, and that's likely how I'd leave my answer. For odds, I don't normally reduce, but you can pretend this is the fraction 2 over 12, and you can reduce it to 1 in 6. For whatever reason, probability fractions are generally reduced. Odds aren't always reduced, but you can. I'll take either for odds. So you should be able, hopefully, to do B and D with that kind of talk up. And I'll move on to question 2. And in question 2, we have a box of marbles. And this box has 9 red marbles, 2 blue marbles, and 3 yellow marbles. So it has a total of, 9, 11, 14 marbles. There are odds and probability questions, and odds and probability are similar, but they're different. So it's easy to get them confused, so you need to get good at being able to bounce back and forth between odds and probability. So first question, the probability that the marble is red, well, there's 9 red marbles of the 14 marbles in the box. If I'm selecting one at random, I could get 9 red ones. I'd like to get one of the 9 red ones, but I could get 14, any one of the 14 marbles. So it's 9 and 14. So I just formed a fraction. The numerator has the number of marbles that have the desired look, in this case red, 9 of them. The denominator is the total number of marbles possible, which is 14. To do the odds in part B, I need to separate my marbles into red and not red. And the not is going to go second because it's odd in favor. So for the red, there's 9 red marbles. For the not red, there's 2 blues and 3 yellows. So the odds in favor of selecting a red marble would have the 9 red marbles to the left of the colon, and then the 5 marbles that aren't red to the right of the colon, the 2 blues and the 3 yellows. So the odds in favor of selecting a red marble would be 9 colon 5. You'll notice that in odds questions, the numbers before reducing add up to the denominator in probability questions. Part C, the probability that the marble is blue. The numerator is going to be the number of blue marbles. The denominator is going to be the total number of marbles. So this is going to be 2 and 14. And in probability, we generally reduce the fraction. So for part C, I'd write 1 and 7. Part D of number 2 is an odds, and it's relative to blue, and it's against. So I need to separate the sample space into the not blue marbles and the are blue marbles. And because it's against, I do the not blue marbles first. And for the not blue marbles, there's 9 red and 3 yellow that are not blue. And for the blue marbles, there's 2 blue. So my non-reduced odds answer for part D, there would be 12 marbles that are not blue, the 9 red and the 3 yellow, and 2 marbles that are blue, the 2 blue ones. So this would be probably the answer I would leave, but you can definitely reduce that to 6:1. So again, in a non-reduced odds question, the numbers will add up to the total number in the denominator of the probabilities, or the total number of elements in the sample space. Okay, I'll keep trudging along here, and now we're in cards questions. So in cards questions, we need to understand a deck of cards really well. And so I'm asked to do both the odds against and the odds in favor. Once I have one, I'll get the other one. So for number 4, I'm going to need to do first the odds against selecting a red card, which means I need to break up a deck of cards into the not red cards and the are red cards. In an odds question dealing with cards, the 2 numbers that I put in have to add up to 52 because there's 52 cards in a deck of cards. In the odds questions for my marbles before, my odds numbers had to add up to 14 because there's 14 marbles in that particular box. For the odds question for Anne, the odds numbers before reduce had to add up to 14 because there's 14 bills in her deck. So for each of the card odds questions, I need my numbers to add up to 52 because there's 52 cards in a deck of cards. Now I need to figure out how many cards in a deck aren't red and how many cards are red. So for me, the red cards are all the hearts are red and all the diamonds are red. There's 13 hearts and there's 13 diamonds, and so 13 plus 13 is 26. So for the are red, there's going to be 26. For the not red, the spades and the clubs are not red. There's 13 spades and 13 clubs, and 13 plus 13 is 26. So there's 26 cards that aren't red. So when I go to do my odds, for not red, I'm going to put the 26 cards that aren't red. For are red, I'm going to put the 26 cards that are red. These would be the odds against selecting a red card, which would be 1:1 if you reduce it. I'm asked to do also odds in favor, and I won't do any work. I'll just flip the answer that I got for odds against, because odds in favor of an event are just kind of the reciprocal in some sense of the odds against. So I'm going to switch these numbers, and it's going to look the same. Just in case you're not quite, well, I'll let you take a stab at number 3. And if you can't get it, when you watch me do some of the higher problems, you'll probably start to get it. So for 6, I want the odds against selecting a queen and the odds in favor of selecting a queen. I'll do the odds against selecting a queen first. To do the odds against selecting a queen, I need to separate the deck of cards into queens and not queens. When I do odds, the numbers I put in add up to the total size of the sample space. My numbers I put in here need to add up to 52. For this problem, it's a heck of a lot easier to count the queens. because they're just, you can't hardly see them, but there's 4 queens in a deck of cards. So the number I'm going to put in for the queens is going to be 4. I could now count. There's 4 aces, 4 twos. I could count all the cards that I haven't circled yet, one at a time, to find out the number of not queens. I don't care to do that. So to find out the number of not queens, there's 52 total cards, and 4 of them are queens. That means the rest are, the other 48 are not queens. So if I counted all of these cards one at a time, eventually I'd get to 48 if I didn't make a mistake. So the other number I'm going to put in my odds is going to be 48, because there's 48 cards that aren't queens. So when I'm doing odds with cards, I generally count the one that's easier, the smaller one, and to get the other one I subtract from 52 rather than counting the other, because they're always going to add up to 52. The 2 numbers on either side of the odds in a card problem have to add up to 52, which is the total size of the sample space. And so this would be perfect for the odds against, and if you want to, that reduces to 12 to 1. And then the lovely thing about being asked the odds in favor, it's just the opposite. Odds against selecting, odds in favor of selecting. And I generally don't reduce these, and it's just the way I was taught. And I think that's common. But both of those would be okay. Your answer for number 5 should look remarkably similar to my answers to number 6. Seven is easier than 8. Let me do 7, and then I'll maybe never do 8, because I'm not sure you're ready for number 7 yet, and I'm not sure doing 8 would prep you for number 7. So I'm going to do number 7. I'm going to do the odds against selecting a 7 or a queen, which means I need to break the sample space up into the cards that are not 7s or queens and the cards that are 7s or queens. And I find the one that's smaller to count and isolate it. For me, it's easier to count the R's because there's not that many of them. So I'm going to go to my sample space. I'm going to count the 7s. There are 1, 2, 3, 4 7s. Hopefully you can kind of see that. And there are 1, 2, 3, 4 queens. So in my sample space, there are 4 7s and there are 4 queens. And those are the ones that count to be 7 or queen. You can't be both a 7 or a queen, but this wants to count 7s or queens. There's no cards that's both a 7 and a queen. So this is going to count, for the R, it's going to count those 8 cards, because there's 8 cards in the deck that represent their 7s or queens. And then for the not 7 or queen, I could count all the cards that I haven't highlighted here, or I could just take the 52 total cards minus the 8 that I've highlighted, and that's going to give me 44 cards that I haven't highlighted. That's the 44 cards in my deck of cards that aren't a 7, nor are they a queen. So I'm going to write 44:8, and I can try to reduce that. So 44 divided by 8 equals, math, enter, enter. It's going to be 11 to 2. So the odds against selecting a 7 or a queen are 11 to 2. 11 to 2 are 44:8. And then the odds in favor of selecting a 7 or a queen are just the reverse of this. It's going to be 8 and 44. or 2 and 11. Let me check this real quickly because it's an odd, and anytime I do an odd I can check. So number 7, 48 to 4 against, which is 12 to 1, in favor 4 to 48, or 1 to, 12 to 1 isn't right. It should be 2. This is not, 12 to 1 isn't right. That's 11 to 2. Or is it 12 to 1? 4, oh, this is not even the right answer. Oh, because I'm looking at the wrong problem? Idiot. Sorry. I'm looking at this, and these still aren't right. Those answers are wrong. And they were wrong this morning when I did the video once, and I thought I fixed them, but I didn't. I wanted to show you a correct answer. These answers are wrong. I'll fix them, and they'll be fixed when you get to look at it in the future. So, but you should do that. Every time you do an odd problem, you should check your answer. That way you can get rid of all the mistakes that I have and know that you're right when you're right. And if you get a wrong answer and you don't believe it's wrong, during the first few semesters that I do this material, there's just going to be mistakes. I mean, I do each problem like 3 times and on separate days, but I still make mistakes. It drives me crazy that I can't do it perfect, but I just don't. And when I make a mistake, I tend to make the mistake over and over again, and that's what happened there. But these I believe are right answers. All right, so I'm going to do 10 because 10 and 9 work fine together. So for number 10, I'm going to do the odds against selecting a queen and a spade. So against, I need the not first. And then the R second. So I need to search through my sample space and find the smaller side, which is the R side. So I want to find all the cards that are both a queen and a spade. That's different than or. So to be counted in the R, the card has to be both a queen and a spade. And there's only one card that's going to count for it. So there's my spades, there's my queen. This is the only card that I'm going to count in this problem. It's the only card that's both a queen and a spade. And when it says the word and, you have to fit both the criteria to be counted. When it says the word or, you only need to fit one of the criteria to be counted. So for the R, a queen and a spade, it's going to be 1. For the not a queen and a spade, I'm going to take the 52 cards in my deck, subtract the 1 that I've already counted, and the other 51 cards that I haven't highlighted here they fit that they're not both a queen and a spade. Some of them are spades, some of them are queens, but none of them are both queens and spades. So that would be 51 to 1 on number 10. And then the odds in favor, that doesn't reduce, which is nice. I'm not going to write the whole thing down. I'm going to say the odds in favor are 1:51. For 14, I'll do the odds against selecting the 4 of diamonds. That means I need on one side it not being a 4 of diamonds. Our 4 of diamonds seems stupid, but it's good enough. So I need to separate the 52 cards into those that are the 4 of diamonds and those that aren't the 4 of diamonds. And so again, it's easier to count the R's. And for my deck of cards, there's only one card that satisfies that it's the 4 of diamonds. That's specifically the 4 of diamonds. Again, I can't imagine that seeable, but I've highlighted here the card that's the 4 of diamonds, and there's only one of them. So on the R side of this, there's going to be 1. And on the not side, I take the 52 total cards minus the 1 that fits the criteria, and I'm going to 51. So the odds against selecting the 4 of diamonds is 51 to 1. And then the odds in favor are going to be the reciprocal of it, which is 1 to 51. getting done with the card problems and then into some more complicated dice problems. Okay, so for 14, I'm going to do the odds against a black 4. So I need to separate the decks of cards into not a black 4 and are a black 4. So when I go to my deck of cards, clubs and spades are black, hearts and diamonds are red. So I need the black 4s. For the R black 4s, the 4 of clubs and the 4 of spades count as black 4s. They're the only 2 4s in the deck of cards that are black 4s. The other 2 4s are red 4s. So for my R, a black 4, I'm going to put 2 down because there's 2 cards in my deck of cards that fit R black 4s. And then for my not black 4s, I'm going to go 52 cards minus the 2 that are black 4s. And I'm going to get 50 to 2 for the against. And that can reduce to 25 to 1. Now the odds in favor of a black 4 are, again, it's just going to be the reciprocal. So it's going to be 2 to 50 or 1 to 25. And on probability, you have to reduce on odds. You don't have to, but I guess if you do reduce, you just be consistent with yourself. Okay, so that's an important part of problem, an important group of problems, but not as new. The odds part are new, but the sample space isn't new. The next problems are very new because we haven't got to these yet. And this set of problems, problem 15 and the problem that's going to follow it, problem 16, are going to use this sample space that a pair of dice are rolled. We have a first dice and a second dice, and I kind of pretend like maybe one is red and one is green so you can really tell them apart, but they don't have to be different colors. And what we're going to do is we're going to do 2 things. We're going to record the numbers that come on the dice, and we're going to add the 2 dice up. And then we're going to use the sample space to compute probabilities. And it's kind of nice that we're seeing the sample space now because we're going to see it a few more times in this chapter, and we're actually going to have to construct it ourselves. So when we're asked to construct it, maybe in the next section, at least we'll have something to look back on. I'll pull this sheet out when I get to it. So this sample space has 36 items in it, and I use this table to construct it. So inside the more complicated looking squares are the sample space, and there's 36 items in my sample space, and each item I have 2 things. I have the numbers that are on the dice and the sum of the dice. So this would be first dice 1, second dice 1, the 2 dice add up to 2, first dice 1, second dice 2, the 2 dice add up to 3. This one is first dice 3, second dice 4, the 2 dice add up to 7. You know, first dice 5, second dice 5, the 2 dice add up to 10. So there, if you count through here, there's 1, 2, 3, 4, 5, 6. And if you counted all the different pairs here, the sample size is 36. And in a card problem, the sample size was 52. In card problems, when we're selecting one card, in the probability questions that we did in the last section, probability, the denominator will be 52. In odds questions for cards, the 2 numbers add up to 52. In the dice problem that we did previously in this section, we just rolled 1 dice, and there were 6 items in the sample space. The denominator was 6, and the two numbers added up to 6 in odds. So in a single dice problem, in a probability question, the denominator is a 6. In odds questions, the two numbers add up to 6. Well, in a 2 dice problem is what this sample space is for. In a 2 dice problem, when we're asked probability questions, the denominator of my fraction is going to be 36 because there's 36 items that make up the sample space. When we do odds questions, the numbers will add up to 36. I don't know how obvious that is, but it's important to differentiate between the important numbers based on the kinds of problems. So far, these are probably the most common that we'll see going forward. 1 dice problems, there's 6 items in the sample space. The denominator for probability is 6. For the odds, the numbers I put on either side of the colon add up to 6. For card problems, probabilities, the denominator is 52 because there's 52 cards in a deck of cards. And odds problems with cards, the two numbers add up to 52. 2 dice problems, because the sample space is 36, probability questions will have a denominator of 36. The odds, the numbers will add up to 36. So when I go to answer questions regarding to rolling 2 dice, I have to keep that in mind. If it's a probability question, my denominator should be 36. If it's an odds question, my two numbers should add up to 36 before I reduce. So problem 15 is yours, so you probably have to rewind back to it because I'm going to do problem 16, and you might not be able to do problem 15 at all until I get my work done. So for 16, I'm using the same sample space, and find the probability of a sum being an 8. Well, in my sample space, there's 36 items, so the denominator for a probability is going to be 36. Within that sample space, the numerator for this, because I'm trying to find the probability that the sum is 8, the numerator for my probability question needs to be the number of items in the sample space that fit the criteria. The criteria is the sum is 8. If I look through the sample space, again, that's just interior where the more complicated stuff is. So there's the 36 items in my sample space. The denominator is 36 because there's 36 items in the sample space. The numerator is the 1, 2, 3, 4, 5 items in the sample space that fit the sum as 8. So the probability of the sum being an 8 is 5 in 36. The second question is another probability question. Because it's a probability question, my denominator is going to be 36 because there's 36 items in the sample space. What I need to find is all the items in the sample space that first dice shows the number 2. Notice in part A, I'm worried about the sum. In part B, I'm worried about the number on the first dice. In part B, I'm trying to I'll search to my sample space and find all the ones where the first dice is a 2. And this one right here, 2 and 1 has the first dice a 2, 2 and 2 has the first dice, 2, 3, 2, 4, 2, 5, and 2, 6. Those are the items in my sample space. When I look at them, the first dice is a 2. And all these, the first dice is a 1. All those, the first dice is a 3, and so forth. So to do part B of number 16, I focus on the sample space. I'm not focusing on the sum because I wasn't asked to look for a sum. I'm focusing on the individual numbers that come on the dice. I'm looking for the ones that have a first dice of 2, and there's 6 of them. So my numerator for problem 16 is going to be 6 and 36. And generally we reduce fractions, so I'm going to reduce that to 1 and 6. C is an odds. So the numbers I'm going to put in are going to add up to 36. I need to segment the sample space into a sum of 8 and then the sum of not 8. Because for odds in favor, the not goes second and the positive goes first. Now, I could now just count. So I'm going to count the easier one to count. The easier one to count is the ones that are the sum of 8. So of the 36, there's 1, 2, 3, 4, 5 that are a sum of 8. So the number that goes in for the sum of 8 side is 5. Now, I can, if I want to, I could count the ones that aren't sum of 8s by going through and counting. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. Everything that I circled in black, its sum was a number other than 8. So on the side that says sum not 8, it's going to be 31. Well, that was kind of ridiculous to do. For the sum not 8, the total size of the sample space is 36. There's 5 of them that have a sum of 8, these 5. The difference between the 36 total in the sample space and the 5 that have a sum of 8 are the 31 that didn't have a sum of 8. So rather than circling them all, I'm going to subtract from 36. So I'm going to find the easy number, and then to get the other number, I'm going to subtract from 36 to get the odds completed. Because in my odds here, the numbers have to add up to 36. So I'm going to go through, figure out which side is the not and which side is the positive, count the easier one, and then subtract from 36 to get the other side. Alright, so odds against the first dice rolling a 2. So it's going to be first dice not 2, and the first dice is a 2. So I'm separating the sample space for an odds by the first dice being a 2 or not. Because it's against, I want the not first. So now I'm going to try to find the easier one to count, and the easier one to count is usually the is. So these items right here, those are the 6 items in the sample space that fit the first dice is a 2. So on the side of my odds that has it's okay for the first dice to be a 2, I'm going to put a 6. On the other side, I could count everything that I haven't highlighted yet, but I don't care to do that. On the other side, for the first dice not a 2, I'm going to take the 36 items in the sample space minus the 6 that I've already placed as being first dice being a 2, and I'm going to get 30 for the first dice not a 2. So I'm going to put a 30 over here. This is an acceptable answer. You can divide these by 6. 30 divided by 6 is 5. 6 divided by 6 is 1. That would be okay as well. Okay, E is a probability question. Probability, I form a fraction, and the denominator is 36. The numerator needs to be the items in the sample space that have a sum greater than 9. Greater than 9 doesn't include the 9. So I go to my sample space and I start looking for sums that are bigger than 9, not including 9. And I don't get there very quickly. I don't get there until I get to the bottom part of my graph. On those that I just highlighted right there, all their sums are 10, 11, or 12, which are bigger than 9. The ones that I didn't highlight, the sums were either 9, which isn't greater than 9, or less than 9. So my numerators should be, is that 6 items that I just highlighted? So for part E, the probability, I form a fraction. The denominator of the fraction is the size of the sample space, which is 36. The numerator is the number of items in the sample space that fit the criteria, and that's 6. So it's 6 and 36. And I'm reducing all probabilities that can be reduced. Last one for this, the odds in favor of the sum being greater than 9. So I need to break up the sample space into the sum greater than 9, and then the sum not greater than 9. And then for the sum greater than 9, I know that there's 6 of those. So the number that's going to go on the sum greater than 9 part is going to be 6. The rest of them aren't greater than 9, and to get that how many aren't greater than 9, I take the 36 total items in the sample space minus the 6, and I get 30. So 6 colon 30 would be perfect. And if I want to, I can reduce that to 1 colon 5, because 6 divided by 6 is 1, 30 divided by 6 is 5. All right, so hopefully you can go back and do 15, just in case you don't want to rewind to it. I think I can find it quickly here. So this is what you needed to do for 15. Same kind of feel to it. And again, for me, it's easier to have the sample space just to mark up. I mean, you can just look at it on the screen to find those out as well. But this might be a page that I print out and print out a couple of them, just because I destroy the sample space when I'm doing each question. But there's your question 15 that you need to do. Last few problems are kind of dart problems or spinner problems. Oh, actually there's more. Sorry, there's a part G and part H. Too bad. Probability of not rolling a double. So 8 is a part G is a probability question. So the denominator is going to be 36. And the numerator is going to be anyone that's not a double. A double is like a 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So 1, 1's a double. I'm counting not a double. So I'm going to count that's not a double, that's not a double, that's not a double, that's not a, those aren't doubles. 2, 1's not a double, 2, 2 is a double. I'm probability of not a double, so I'm not counting the doubles. So I'm going to go through and mark up every one that needs to be counted. So because I'm doing the probability that it's not a double, I want to count everything in the sample space that's not a double. So specifically, I count all those that I have written in pink. I'm not counting the doubles. 1, 1's a double, 2, 2's a double, 3, 3's a double, 4, 4's a double, 5, 5's a double, and 6, 6 is a double. There's 6 that I'm not counting, so I have 30 that I am counting. So the probability of not rolling a double, I want to count all the items in the sample space that aren't doubles. They're highlighted in pink, and there's 30 of them. It would be easier to count the doubles and subtract from 36, because if you take the doubles away from the 36, you're left with the 30 non-doubles. But if you count up what I have in pink there, there's 30. So the probability of not rolling a double is 30 and 36. 30 divided by 6 is 5. 6 divided by 6 is 6. The odds in favor of the sum being an odd number. So we need to break the sample space into sum being odd and the sum not being odd. It's a little bit trickier. There's a lot to count on both sides. So I'm going to go through my sample space. Because it's odds in favor, I did the not second and the positive first. And I'm going to go through my sample space and find every one of them that has a sum of an odd number. And let's see if I can do that. And I'm just looking at the sums. So that's a sum of 2, I'm not counting it. This is a sum of 3, I am counting it. Sum of 4, not counting it. Sum of 5, am counting it. Sum of 6, not. Sum of 7, am. Sum of 3, yes. Sum of 4, no, because 4 is an even number. So I'm just going to highlight all the ones I'm going to count. Kind of forms a checkerboard. So every one that I'm highlighting, what it has in common is that the sum of the 2 dice is odd. The ones that aren't highlighted, the sum of the 2 dice are even. If you count those up, there's 18 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So for the number of sums being even or odd, it's going to be 18. And always for the other side, I can just take the total number of the sample space, which is 36, minus the number I've just placed in. And that's going to give me the other side. Because there's going to be 18 of them that aren't odd. There's 18 odds and 18 evens. And the not odds are these. And there's 18 of them. So I could count too if I want to count, or I could subtract to get the other number. So 18:18 is the odds, and that reduces to 1:1. Again, I'm consistent on my probabilities that I reduce the fractions, but I'm not consistent on my odds. In fact, I normally don't reduce the odds. That's how I was taught. I'll do 17A just so you have a shot at 17B. So there's a class with 30 people, 16 men and 14 women. Find the odds against, and I'll do selecting a woman. So I need to break the class up into not women and women. And because it's odds against, I did the not first. And then how many people in the class aren't women? Well, the 16 men aren't women. And how many are women? The 14 are women. And I probably reduce that, so hopefully I have a reasonable answer back here. So on number 17A, or 16 and 14, then I reduce that to 8 and 7, and that's completely fine. So hopefully you can do part B with that as an inspiration. And maybe you could have did part A without me even just doing it for you. The last few problems are using a spinner that we used in the last section. The spinner needed to be broken up into 4 equal spots. There's a red, a blue, and 2 purples. And we're doing odds. For 18, I do the odds in favor of landing in a purple. So I need to separate the sample space into purple and not purple. And because it's odds in favor, the not came second. And if I count the purple regions, when I make the regions the same size, there's 2 purple regions, and there's red and the blue, there's 2 non-purple regions. So I'd say the odds are 2 to 2, which I can reduce to 1 to 1. And then, same thing here. For 20, the odds against landing in the red, I need to break this up into not red and red. I did the not first because it's against. For red, there's 1 red section, and then the other 3 sections aren't red. So for 20, the odds against landing in the red region are 3 to 1. I don't know that this was infinitely better than my first lecture, but it was definitely better. So, let me know if the lecture just was kind of not good. I'll make a third stab at it, but hopefully you're able to get through these problems with my second lecture, and nobody will ever see my first lecture. So we're getting close to the end. Just a handful of sections to go. Each section has its own little newness to it. They fit together, the sections, and they don't fit. So hopefully you can just kind of go through these like you did the rest of the semester, and